This is Mrs. KJ going over the 2.09 Colligative Properties. The properties of a solution often differ from those of a pure solvent. The properties of a solution are different from the properties of the pure solvent that is used to make up the solution. So in other words, the properties of water are different than the properties of lemonade, even though lemonade has water in it. The addition of a solute to the solvent will create a mixture of different properties, and that's called colligative properties. This lesson will examine the colligative properties. Colligative properties depend on the moles of substance. They include boiling point elevation, freezing point depression, vapor pressure lowering. Goals for this lesson: describe these colligative properties of solutions: vapor pressure lowering, boiling point elevation, and freezing point depression. Analyze the relationship between concentration of a solution and the effects on vapor pressure lowering, boiling point elevation, and freezing point depression. So there's the student guide, and then from the student guide, I simply copy down what we just read and keywords and pronunciation. Boiling point elevation: the raising of a solvent's boiling temperature based on the amount of solute it contains. So in other words, instead of water boiling at what temperature? 100 degrees Celsius. We would say that we elevate that, and we would say it boils at, let's say, 110 degrees Celsius. So pure water boils at 100 degrees Celsius, but when we have it in solution, we might have a boiling point elevation or increase, and so it would boil at 110 degrees Celsius. Colligative properties: a property of a solution that is the result of the amount of solvent in the solution. It includes a higher boiling point, a lower melting point, and a reduced vapor pressure. In other words, it changes based on the concentration of the solution. So if we have a lot more salt in the solution, then it's going to have different properties or different boiling point than if there's just a tiny little bit of salt. Freezing point depression: the lowering of a solvent's freezing temperature based on the amount of solute it contains. Freezing point depression is the difference in temperature between the freezing point of a solution and the freezing point of the pure solvent. Salt lowers the freezing point. So instead of freezing at 0 degrees Celsius, which is what pure water does, when you add salt, it can freeze at -2 degrees Celsius. Some physical properties of a liquid solution are different from those of the solvent. Why does fresh water freeze before salt water? What keeps antifreeze from freezing in your car? And why does adding it to a car engine keep the engine from overheating? The answers can be found in examining the colligative properties of solution. The colligative properties of a solution are those linked to the amount of solute that is in a particular solution or in the solvent and to make a solution. The water in pine needles does not freeze in winter, which is why pine trees can keep their needles all winter. Freezing point depression is one type of colligative property. So let's look at the picture. A salt crystal on pavement helps melt the surrounding snow. Salt is poured on icy roads to help melt the ice or prevent ice from forming. When liquid water freezes, its molecules form an orderly pattern of a solid. If a solute like rock salt is added to liquid water, the formation of the regular pattern of the solid is disrupted by the presence of the sodium and chloride ions. More kinetic energy must be removed from the solution to make it freeze. The result is that the freezing point of this water and salt mixture is lower than the freezing point of pure water, basically because the salt is in the way. This is the property of the solution, a colligative property called freezing point depression. So the freezing point is depressed or lowered. Freezing point depression is the difference in temperature between the freezing point of a solution and the freezing point of a pure solvent. By the way, adding salt only lowers the freezing point a few degrees, which is why sometimes we still have icy roads even though they put salt on, because salt water will still freeze. There are many common instances of freezing point depression. When you add salt to ice, you lower the melting point of the ice. If the freezing point is depressed enough, the ice will have a lower freezing point than the outside air and will melt, making your sidewalk safer. Ice cream makers take advantage of this colligative property by filling part of the container with salt and ice mixture. The temperature of the container then can go below the freezing point of water, and when it does, the cream will solidify into ice cream. So if you just put cream in regular ice, it won't freeze. You have to make it less than 0 degrees Celsius. You do that by adding salt, and then you can make ice cream. Boiling point elevation is another example of a colligative property. So boiling point, elevation, elevate meaning being higher. You may have seen a car pulled over on the side of the road, its hood wide open, with steam billowing from the engine. That car was overheating. Chances are the driver did not have enough coolant in the car's cooling system. Coolant is a solute. When coolant is added to the water in the car's cooling system, it raises the boiling point of the water, making it less likely to boil over. This raise in the boiling point is a colligative property called boiling point elevation. Antifreeze does the opposite. It may in fact be the exact same chemical or set of chemicals as the coolant, but it is a solute nonetheless and thus can act to raise the boiling point or lower the freezing point. As the atmosphere reaches the freezing point of the solvent, the presence of the solute depresses the freezing point of water in the cooling system, making it less likely to freeze in winter temperatures. Ethylene glycol, the active chemical in antifreeze, keeps the water in antifreeze from freezing and makes it a more effective coolant. So in other words, it does both. Vapor pressure is determined by the evaporation rate of a solution in a sealed system. Okay, so remember evaporation happens at all temperatures when a substance is a liquid. Basically, the molecules are bouncing around, and when they get to the top, woohoo, they become free and they become a gas. Vapor pressure is the force exerted by a gas that lies above the solution in a sealed system. So it's the pressure of this gas because we have a sealed container, and this gas is over top the solution. In a pure liquid, there is a point when molecules on the surface of the liquid evaporate. At the same time, molecules that are in the gaseous phase will condense into a liquid. So you've seen this before. Water evaporates, but then sometimes it hits the top, and if the top of the container is cooler, it condenses and it will run down the side. So at the same time, molecules that are in the gaseous phase will condense into a liquid. When the rates of these two processes are equal, the system is in equilibrium. The pressure on the surface of the solvent at that equilibrium point is called vapor pressure. Vapor pressure is caused by molecules pushing down on the surface of the liquid. So I added vapor pressure is determined by the evaporation rate of a solution in a sealed system. Vapor pressure is caused by molecules pushing down on the surface of the liquid. And then I basically just put the whole paragraph here because this is one of those where we don't hear it very often. And then I just underlined the key parts. So it's got to be sealed. Molecules on the surface of the liquid are evaporating. Same time, molecules that are in the gaseous phase will condense into liquid. When the rates of these two processes are equal, the system's at equilibrium. The pressure on the surface of the solvent at that equilibrium point is called the vapor pressure. The addition of a solute to a solution decreases the surface area exposed to the air for evaporation. Okay, so if we look at this picture, all across the top there's water. Okay, so evaporation can happen everywhere across there. But here, oh, look again, that solute's getting in the way, and that's going to make a difference. When a solute is added to a pure liquid, the vapor pressure drops. What happens is that the molecules of dissolved solute take up some of the space at the top of the liquid. This prevents some of the solvent molecules from evaporating, but the rate of the molecules condensing does not change. Because see, there's just the gas up here, so they can still hit the top, condense, and roll back down the side. There is an imbalance with more molecules at the interface of the liquid phase than the gaseous phase. More molecules of gas leave the air than enter it, the vapor pressure drops. The amount of surface area available for the escaping solvent molecules is reduced because some of that area is occupied by the solute particles. Only non-volatile solutes. Vapor pressure lowering will occur only if the solute that is added to the pure solvent is non-volatile. Non-volatile means that it does not easily vaporize. A substance such as gasoline does vaporize and therefore will have less of an effect on the vapor pressure of the solvent. Compounds such as sodium chloride, salt, and calcium chloride do not vaporize readily. The addition of either of these two substances to a solvent will lower the vapor pressure. So in other words, they're putting salt here, which isn't going to evaporate, so it just gets in the way. If this was gasoline, it would also be evaporating and bouncing around up here, and it really wouldn't cause much of a problem. All right, so let's add this to our notes. Again, I think this one's worth putting the whole paragraph in because you really don't hear of this that much, and then go through and underline some key parts. So I bolded this sentence, when a solute is added to a pure liquid, the vapor pressure drops. I added the sentence, the solute gets in the way of evaporating since it is taking up some of the room on the surface. And then you can go through, and the other key point is the rate of molecules condensing does not change. So you have an imbalance, and that's going to cause your vapor pressure to drop. The number of moles of solute is the key factor in determining the effect on a solvent's colligative property. The quantitative measure of colligative properties, such as boiling point elevation or increasing, freezing point depression or going down, and vapor pressure lowering, depends on the number of solute particles, not on their actual chemistry. This may be counterintuitive. It seems that colligative properties would be related to the chemical nature of the solute being used, but that's not the case. When sugar or salt is added to water, the freezing point decreases and the boiling point increases. The key quantity is the number of moles of solute. Sugar does not dissociate in water. It stays together as a single molecule. So 1 mole of glucose contributes only 1 mole of substance to a solution. 1 mole of sodium chloride in solution contributes 2 moles of substances. How? You get 1 mole of Na and 1 mole of Cl. Therefore, a molar amount of NaCl will have twice the effect on a solution's colligative properties as an equal molar amount of sugar. Basically, it dissolves, so you have twice as many pieces. Sugar stays together, it's just one piece. Salt contributes more moles per volume than sugar does because salt breaks into sodium ions and chlorine ions. So if you notice, it's Na plus and Cl minus. So I wrote the quantitative measure of colligative properties depends on the number of solute particles, not on their actual chemistry. NaCl breaks into Na and Cl in water, whereas sugar stays in one molecule, so NaCl counts twice as much. So again, you have 2 pieces getting in the way instead of 1 piece getting in the way. Colligative properties are unique for each solvent. Each solvent has its own value, abbreviated as capital K, for how the addition of specific amounts of solute will change the freezing point, boiling point, or vapor pressure. The units for K are degrees Celsius over m, where m is the molal concentration of the solution. For example, for every mole of solute, the freezing point of 1 kilogram of water will change by negative 1.86 degrees Celsius. You can calculate the effect of a solute on a solvent's temperature by multiplying the K value by the molality m. For example, elevation and boiling point is the change in the temperature of the boiling point equals the K of the boiling point times the molality. Depression and freezing point equals the change in temperature of freezing point equals the constant of the freezing point times molality. Freezing point depression and boiling point elevation constants for some common solvents. So in other words, 1 mole makes water change by negative 1.86 for the freezing point. Look at how much 1 mole of salt changes acetic acid. It changes it a total of negative 3.9. Look at how much it changes benzene. Again, adding 1 mole of salt to any of these will have this effect. Changes it by negative 5 degrees. It changes phenol by negative 7 degrees. We can also see how much it changes the boiling point. If I add 1 mole of salt to water, it changes the boiling point by half a degree. For acetic acid, it changes it by 3 degrees. For benzene, by 2.5 degrees. And for phenol, by 3.5 degrees. I just added that whole slide to my notes because I thought it was helpful. And then here is the last slide. Go ahead and read it yourself because I'm about to run out of time, and that should be it for this lesson.